This is geometry lesson 7.5. We're going to be looking at the SsA condition and the HL congruence theorem. So the big idea says the abbreviations of capital S, small sa, and HL stand for two other combinations of measures, corresponding sides and angles, in two triangles that are sufficient for the congruence of the triangle. So we've looked at SSS, ASA, all of those theorems. And we've talked about how SsA is actually not one of those. We're going to talk about a special case where this actually is true. So it's not true in general, but there is a very specific time that it actually does work. So that's what we're going to be looking at here today. So we're going to start with the SsA condition. Now, obviously, if you spelled this backwards, we have a word that they don't want standing for something in school, but that is the same thing depending on which way you go there. So that's side angle. As you look at these pictures, you're given two sides and an angle that's not included. That's the difference between this and, say, SAS. So this is not SAS, where A is the included angle, meaning between the two sides. If I had two sides and then angle B, that's side, angle, side. This is angle, side, side, or side, angle. So as we look at these, I've drawn, well, I haven't, but I've given you these two pictures that show you why this in general does not work. If given two triangles where you have, say, 45 matching angles, and then two congruent sides, they are not necessarily congruent triangles. So that's how come we have not used SsA as one of our theorems. You've got the equal 45. You've got this equal side, AB equals XY. And BC also equals YZ. So you can see if I swing this in, I can then swing that out, and it looks like this. So if I draw this right here, that's showing you what BC is. Or if I extended it this way, that's showing you what YZ is right there. So just because I have this angle and then two equal sides, obviously these two triangles are not congruent, but they have the same angles and they have the same side lengths. So that's why in general, SsA is not a condition that we use. Okay, but there is a time when this does determine a unique triangle. So here's when this works. And you'll notice how up here we just talked about it with the capital letters like we're used to, but we're actually going to lowercase this middle s, and there's a reason for it. So it says if two sides of the angle opposite the longer of two sides in one triangle are congruent respectively, blah, blah, blah. This is just going to confuse you. It's math jargon. So basically, this condition, SsA, works if when you're given these two other sides and the angle is not included, if out of those two sides, the longer of those two is across from the angle. Okay, and that's why they label it like this, because as you work your way around, it's the angle, it's the small side, it's the big side. The angle, the small side, the bigger side. If that condition is true, then we actually can use this congruence theorem. Okay, so there's enough information to prove that these two are congruent to each other, even though it's SsA, which normally does not work, because the longer of the two congruent sides is across from the angle, not next to it. So if the bigger side was next to the angle, then I don't have enough information to show that this is true. All right, now we're really hardly ever going to use that specific theorem. We're going to be much more often using the HL theorem, which is what we're mainly going to look at today. But this comes from this one. So we want to look quickly at this special condition where SsA works. And now we're going to study a more common special case, the HL condition. So we're going to be looking at triangles that have 90-degree angles. Right triangles. This condition only works in right triangles. It actually is the SsA theorem. Okay, so it's the hypotenuse leg condition. That's what HL stands for. So you've definitely studied this at one point in algebra. You even talk about this. When we have a right triangle, we have two legs. And then the longer side, which is always across from the 90, is called your hypotenuse. So what this theorem says, if you have two right triangles and you have a congruent leg and you have a congruent hypotenuse, that's enough information to say that those two triangles are congruent. Here's why. This actually is the SsA theorem. But if we have a 90-degree angle in a triangle, that has to be the biggest angle because there's only 180 degrees to go around. So if this is 90, the other two together have to add up to 90. So this has to be the biggest angle. So therefore, that SsA special condition that we need, where the biggest sides across from the angle that's given to us, is going to happen automatically every single time in a right triangle. Across from the 90 is always the biggest side because 90 is always the biggest angle if it exists. Okay, so this is the SsA special condition. Longest side across from the angle. Smallest side is the one that's next to the given angle. So this is SsA. But when we look at this with a 90-degree angle, we're just going to call this the HL theorem for hypotenuse and leg. And this explains that. So let's use it a little bit on the back. All right, example number 1. So this example is going to ask you to explain it. We're going to do it as a proof, just so that we can continue to practice that. But if this was the type of question you saw, you could explain it in words. You basically would go through the proof and just write sentences out explaining your conclusions and your justifications. So to simplify it, we are just going to do a proof. Okay, and this is going to involve our HL theorem. That's what we're going to be looking at here today. So it says AB, this line right here, represents a vertical radio tower. Okay, so that gives us some information there. If it's a vertical radio tower, then that is going to be hitting the ground at 90 degrees. It's not on a slant, it's straight up and down. That's what vertical means. So I automatically know that these angles here are 90. Okay, so angle ABC has to equal angle ABD, and they have to equal 90 degrees. That's part of the given. Okay, so I'm going to put that right here. Angle ABC is congruent to angle ABD. When they tell us that this is a vertical radio tower, they've given us the fact that those are 90 degrees, so that's going to be part of our given. They want you to explain why these guy wires AC and AD of the same length. So they're telling you AC is congruent to AD. So I can put that here in my given. So through that sentence, we've got all of this given to us. They want you to explain why these wires, which are the same length, will reach the ground at the same distance from B. So they want you to explain why these distances where the wires hit the ground have to be the same distance away from the pole. So they're asking you to prove that this distance, BC, is congruent to BD. They didn't write it out like that, but that's what they're asking. Explain why these wires, which are the same length, so it's given to you that they're equal, will reach the ground at the same distance from B. So prove that those distances BC is congruent or equal to BD. So we've already got two pieces of information to prove that these triangles are congruent. Let's mark it in the picture. AC is equal to AD because they said the wires are the same length. Okay, and we have these 90-degree angles, which are going to be equal to each other because we know this is a vertical tower, which is always going to hit the ground at 90 degrees, right? It's not going to lean one way or the other by design. All right, so if we have a 90-degree angle, we have a right triangle, so all we need is the hypotenuse and the leg. So we've got the hypotenuse, that's what's across from your 90. So we just need either one of these legs. Now we're trying to prove this one, so obviously we're not going to have that one as part of our proof until we get to the end. And so we're going to use this shared side of AB as our leg. So we have the hypotenuse and the leg. This is side-side angle, which we call the HL theorem for a 90-degree right triangle. So all we have to say here is AB is congruent to AB. That's the reflexive property. which we've gotten used to using now. And so now we have three pieces of information. Equal angles, which are 90 degrees, AC equals AD, and then AB equals AB. We have side-side angle, which is your hypotenuse leg. So now we have enough information to say that these triangles are congruent. So ABC is congruent to ABD. Make sure that they match up with the corresponding vertices. And now this is where we normally would say SAS, SSS. So now because we have that 90-degree angle, this is our HL theorem. And just like we just say SAS sometimes, you can just say HL. That is perfectly fine. And now all we've done so far is proven that these two triangles are exactly the same. But if that's true, then this has to equal this. If these two triangles are congruent, their corresponding parts are also congruent. So now we can say BC is congruent to BD by CPCF. Corresponding parts of congruent figures are congruent. All right, so down to the bottom, we have a straightforward proof in terms of how it's given to us. So our given is that this is a circle with center A. So I know anything that goes from A to the outside is a radius. They tell you have diameter BC, which is just kind of extra information. Once you know this is circle A, we know that this is the diameter here. I guess it's showing you that these are going to hit at 180 degrees here. There is no slight angle there. So they give you that BC is the diameter, which is going to be important. We're going to be using inscribed angles here. And then they tell you CE equals BD. So let's mark that in the picture. CE equals BD. Now, you know we're in this section where we're looking to use the HL theorem, which is where we're looking for right triangles. So we've got these angles here. We're going to need to show that those or prove that those are 90-degree angles if we're going to use the HL theorem. Otherwise, we can't use it. So here we got conclusions and justifications. And we'll put our given up here. So we're going to put all of this in here with the given. All right, and so out of those triangles, we only have one piece of information so far that can help us get to our final conclusion. Now look what we're trying to do. We're trying to prove that CD is parallel to EB. The way that you prove something is parallel is you show that like alternate interior angles are equal, corresponding angles are equal, same side interiors are supplementary, right? If you have two lines and they're being cut by another line, if you can prove that the alternate interior angles are equal, then you can prove that those lines are parallel. So that's our goal here. But first, we got to prove that these two triangles are congruent. And so we have to focus on these angles. Until we know these are 90, which we have not been told yet or proven yet, we can't use the HL theorem. Now, if you look at these angles, they are inscribed angles. This angle E right here and angle D right here. Right? They hit the side of the circle and then they go out. So remember, we've studied inscribed angles are half the size of the arc that they intercept. So angle E is going to hit at B and C, and D is as well. Hits at C, hits at B. CB is the diameter. BC is the diameter. They told us that, which means you've got half the circle on one side, half the circle on the other. Okay, so from C to B, that entire arc has to be 180, and it's 180 on the other side. So if this inscribed angle is hitting that arc of 180, it's half the size. It's 90. So we can say that this angle is 90 and this angle is 90. Therefore, they're congruent to each other. So we're going to say angle E equals, notice I said equals, not congruent, equals angle D, which equals 90 degrees. So we say congruent when we don't know the exact measurement or degrees, but we do in this case. It's 90. So we don't have to say congruent. We can just say equals. If all we knew is that they're the same size, we say congruent. But since we know that they're actually equal to 90 degrees, you use an equal sign here. All right, now we have to kind of write this out. And so you can say that they are inscribed angles are half the size of their intercepted arc, stuff like that. But you can say they are inscribed angles of the diameter. Okay, you don't have to memorize that. Something along those lines. You can explain this in words. It doesn't have to be some perfect word for word memory thing that you have. Just explain that it's an inscribed angle to a diameter. Therefore, I know it's 90 degrees because it's half the size. And if you wanted to get even more specific, you could write that out. All right, so now I've got almost enough information for hypotenuse leg theorem, HL theorem. I've got the 90, and these are legs. They're coming out from the 90. So what I don't have is the hypotenuse, which is BC. Both triangles use BC as their hypotenuse. So it's going to be equal in both of these. They share it, so this will be a reflexive property. BC is congruent to BC. By the reflexive property, they are sharing that, and now I have a 90-degree angle, a leg, and the hypotenuse in both triangles. So now I know that those triangles are congruent to each other. So I have to state that. Triangle, I'm going to go from the 90. D, I'm going to go across this side that I have. B, C, it's congruent to. So again, I'm going to start with the 90. E, go across that leg that I've got. C, B. Okay, by the HL theorem. Now from that information, I can say any of their corresponding parts are equal. So in order to make these lines parallel, I need to prove alternate interior angles or something along those lines are equal. So these are the lines I'm looking at. CD and EB. So they're being cut by these lines CE and DB, right? And we know that's going to hit at 90 degrees there. But if you take a look, these angles of the triangle, these matching angles right here, that one and that one, those have to be equal to each other if these two angles are congruent. And those are alternate interior angles as this line is hitting your two parallel lines. Those are alternate interior. So if those are equal, that means we have proven that these are parallel. So we got to do that in 2 steps here. So first, step 5, we're going to say that those angles actually are equal. So angle DCB, that's this one, DCB, is congruent to angle EBC. And the reason I know that is not because they're alternate interiors, so be careful. That's not why I know they're equal to each other, because I haven't been told these are parallel yet. The reason I know these are equal is because they're corresponding angles of these two triangles, which I've already proven are congruent. So this is CPCF. These angles are equal because they're corresponding parts of congruent figures. Now that I know that they are equal, alternate interior angles are equal, therefore those lines are parallel. So now I can prove CD is parallel to EB. Now you can say the alternate interior angles theorem. That's perfectly fine. I'm going to kind of just explain it using those words. I know these are parallel because alternate interior angles are congruent. So since I have found alternate interior angles to be congruent, I know those lines are parallel. I've proven what they've asked me to prove.